Hello. That's good energy. My name is Daniel Moth, and it is my great pleasure to welcome every single one of you to the first session on the third day of PDC 2008. As you can see up there on your screens, I work for the parallel computing platform, but before that I used to work and live in Europe. And it's a coincidence that exactly a year ago from this week, the parallel computing team sent me something that blew my mind. They sent me a technology called the parallel extensions to the .NET framework. Now, I was so excited with this technology and the area it is trying to address that, do you know what I did? I quit my job, left the country, emigrated to the US to join the product team to contribute towards the vision of bringing parallelism to the mainstream, parallelism to the masses. And that's the profound effect this area of computing has had on me, and my hope is it will have a similar effect by the end of the session on you. I don't mean that you need to quit your jobs and leave the countries. Right? Some food for thought, maybe. So I mentioned there the parallel extensions to the .NET framework. Can I ask how many of you have heard, not necessarily downloaded, but heard of the parallel extensions to the .NET framework? Show of hands? That's great. That's many of you. And for those of you that didn't put your hand up, that was more for my curiosity. I'm going to start exploring this technology in this session starting from scratch. Because the parallel extensions to the .NET framework, which we released a CTP of last year and earlier this year in June, we're announcing are part of now of .NET Framework 4. And .NET Framework 4 will be released with Visual Studio 2010. So before we go and dive into that, you're probably wondering, what else are we doing in the parallelism space in Visual Studio 2010? So I have a picture here with some technologies we're releasing as part of this major release. And I should tell you, the work that Microsoft is doing in this space is a lot bigger than the stuff that I've added on this slide. For example, you're not seeing on this slide technologies like the CCR, or upcoming IFX and Maestro, or things like incubation technologies in software transaction memory, or maybe things that we do across multiple nodes, HPC, MPI, MPI.NET, technologies like that. I've only included the technologies that we're shipping out of the box with Visual Studio 2010. And I'm not going to cover all of them in this session. We just don't have the time. In particular, I'm not going to be touching any of the native APIs we're offering for parallel programming. There are equivalent native APIs to the managed that I'm going to show you here. And Rick Molloy covered those in his session on Monday. You can watch that recording online if you didn't get to attend the session. I'm also not going to be covering the native engine, the concurrency runtime that sits under those native APIs, because Nicholas Gustafsson will be covering those later on today, if you're interested in that. And finally, on the tooling front, I'm not going to be covering the profiler, the new profiler enhancements that we have, because Hazim Shafi covered those on Monday, and you can watch that recording online as well. So in this session, we're going to look at the rest of the stuff that has stayed in color on this slide. But again, before we go and dive into that, some of you are probably thinking, what is this parallelism thing exactly? You know, can I see it in action? What do you really mean? So let's go and have a quick look at what we really mean. So here I'm running on a remote desktop into a machine that, like all the ones we have back at home in the office, I'm sure, has 16 cores. So it's 4 sockets, 4 quad cores, and in a total, 16 cores. And what I want to do is run a client application on here that I've developed previously and see how it performs, you know, because with all this computing power, surely it's going to be faster, right? So we go and run up this application that I have here, and this is the ray tracer. And it's called a ray tracer because when you kick it off, it does some ray tracing. And if you look at that, you see that the image, it's a bit choppy, you know, it's not ideal. And you can look on the title bar and see that we're getting frames per second, about 1.8. And when I look at how much power I'm using up here, and you look at the percentage, I'm really only using 1 core. That's what's happening here. And that's exactly what's going to happen to all of your applications when you move them to a machine that has multiple cores. It's not magic. It will still continue to run on a single core. So the question is, how can we make an application take advantage of multiple cores? And the answer is, we go and stop it and check a box. When I check the box, it's going to go and take a different code path. A code path that offers this smooth animation. A code path that offers you 20-something frames per second. A code path that uses a lot more of the compute power I have on this machine. So now the questions on everyone's mind is, what was that code path? What are you doing in code to make this happen? And that is what the rest of the session is about. So let's go and stop this guy and go back to the slides. Notice the picture I have on this demo slide here. Can you count the cores on this machine? 64. Right? This isn't, I made a joke earlier, a throwaway joke, that we all have 16-core machines. I know we don't, but if we are to believe the hardware manufacturers, we're going to be seeing 80, 100-core machines on mainstream desktop machines. Right? We cannot make a CPU go faster, but we can add a lot more of them on a box. So it is not just a desire to move to parallel programming. We must move to parallel programming. The question that you have to answer, and this is for you to answer, is when will you do that? We think you should do it now. So we're going to go and explore that. When people think of parallelism, and I show a demo like this, most of you are probably thinking of threads. So I just wanted to clarify a difference, in my opinion, between threading, concurrency, and parallelism. How many people in here are familiar with threads? You're comfortable with threading? Can I have a show of hands? Again, that's most of you. So I can bet, even though I don't know you, that when you use threads, you typically use them in order to maybe improve the perceived performance of an application. Maybe do some async operation. Maybe improve overall performance by hiding latency, making a web service call, a disk I/O. So we use threads in those scenarios typically, and that brings synchronization issues in, and most threading talks focus on synchronization issues because, that's what gets introduced. The question is, on a multi-core machine, what happens? Everything I've just said is true, the opportunities and the challenges, but additionally, you have an opportunity to improve the actual performance of your compute-bound operations. And there's not many people that use threads for that particular goal. Another way of putting it is, if what you're doing makes complete sense on a single-core machine, then it's probably not aimed at parallelism. Parallelism can only happen on a multi-core machine. Another way of putting it is, you can have concurrency on a single-core machine, but you can only have exploitable concurrency on a multi-core machine, or parallelism. So, assuming that was all understood, how are we going to spend the rest of this session? Well, I hope I've set the scene. And then we're going to go and look at these agenda items that you can see up there. As you can probably tell, I'm going to try and introduce some new concepts, but actually behind those concepts, it will all be code. In this session, there are 50 minutes of demos. So if you don't like code, I'm going to have to say now, please, there are doors at the end of the room. There are other sessions here. Please invest your time correctly. I don't want you to waste your time here. A lot of code. And it's going to be managed code. I happen to be using C#, but everything I'm going to show you works in VB and any other managed language. You're going to see how easy it is. And the reason for that is because the support we have added is at the library level. We haven't changed language or the compilers. We're adding support at the library level. So any managed language can use this. So is this OK with everyone? Can we proceed on this basis? Yeah? And nodding is one way you can communicate with me in such a big room. Or you can shake your heads if you think no, or interrupt me with applause at any moment. That's fine as well. That's all great. Too easy. So let's go and have a look at a demo. So over here, I'm running on my laptop, which is a quad-core machine. And I have here a Visual Studio 2010 .NET 4 C# console application. And as you can see in here, all I have is 2 code files. So let me show you these 2 code files. We'll start with tree. So this is a tree. It's also a tree node at the same time. It has 2 properties, left and right. I know how to spell that, but I prefer saying right. I'm just strange like that. So we have left and right, and each tree node has data, an integer. So this is the data structure we'll be using in this particular demo. I also have here something that wouldn't typically exist here. It's just a helper method for my demo, which is create some tree. So given a depth of 3 and a start of 1, it would create a tree that looks like that. So it's balanced. Each node would have 2 children, left and right, and each one of those nodes would go further depending on the depth I've given. And the values would increase, 1, 2, 3, 4, and so on. So that's what this is doing. So let's go and use this. The way I'm using this in my program file is by having 3 methods. If we look at the entry points, all I'm doing here is creating that tree with a depth of 9 and starting at 1. So I'm going to have 1,023 nodes. I didn't do the math now. I did it earlier. So we have 1,023 nodes. And then we're going to go and call walk tree, passing in that tree. And you can see that method here. I'll show it to you in a second. Notice that before I start the stopwatch and after I go and get how long it took to execute that. I'm not looking for precise numbers here. Just a rough estimate is good enough for me. And then we're going to go and wait. So what do we do in walk tree? In walk tree, we're going to go and process the item. So we're going to process the data. And we're going to see that in a second. But I want to process every node. So for that reason, I'm using recursion here. So I'm going to call walk tree left and right. And then at some point, there's not going to be any more children, so it's going to get out of there. So that's the way this works. So the question is, what do I do in process item? This is where my compute-bound operation lives. And for demo purposes, I'm just wasting time. I'm just spinning for no reason whatsoever. This is where you would have your real code that you want to make go faster, I guess. Also notice that this method here returns the integer, but I'm not using that at this stage of the demo. So just note that and leave it aside. OK, so how long do you think this is going to take to run on this quad-core machine here? Let's go and fire it up. Notice that I'm only using 25% of the CPU. I've got 4 cores, 25%. Really, I'm only using 1 core. And in a minute, we're going to see, in 15 seconds approximately, we're going to see the value being printed out, how long this is taking. And there it is. So let's go and capture this value for posterity. So we'll go and write it over here. And I have set my performance goals, and this does not meet my performance goals. So what must I do? Well, the first thing I must do is go and optimize my actual algorithm, my business logic. So let's say I've looked at this, I've tried to optimize it, I cannot spin any faster. So what I have to do now is go and find another way of taking advantage of the multiple cores here. So I'm looking at this, I have a big chunk of work, and I need to partition it somehow. So I look at this and I think, well, you know what? I could actually walk the left and the right separately using threads. So let me go and do that. And don't try this at home. I'm a trained professional. You do not want to try this. So let's go in here. And I'm going to use a Lambda. Could have used a delegate explicitly, an anonymous method, all kinds of different things. And then we're going to go, of course, and start the thread. Creating it on its own won't do much. And I want to do the same for the right-hand side. So let's use here a clipboard inheritance and do that. We're going to go say Rai, take this guy, do that, and I'm done. So with this, is this functionally equivalent to what I showed you earlier? No. Earlier, we were processing the left and right, and only then we would go and reach this statement. Right now, the way I've done it, it would work, but actually it wouldn't be functionally equivalent, because we would reach this statement before processing left and right. Does that matter? Well, let's assume it does, because that's what the previous algorithm was doing. And in some scenarios, it would. So how can I fix this? Well, I can go and wait for the thread to actually finish. And now, these two are functionally equivalent. And I've partitioned my work. Will I see a performance gain here? Let's go and build it. It builds. We have compilation. And then let's go and bring this guy up, run it, and see. So now I'm using 100% of the CPU usage. I'm using the machine in such anger that it actually paused there for a second. And we're going to see how long it takes. It took longer. Why is that? Too many threads, too many garbage collections. Let's go and run it again. I can make this actually work. Like I said, don't try this at home. Now what's the exception we're going to see? Anyone? The exception that I'm going to see if I click cancel? Out of memory. What's going on here? Why doesn't this even run on the machine? When you use threads, you're actually using, for each thread, 1 megabyte of committed memory. Right? So 1,023 threads for each node that I had. You do the math. So depending on what else is running on the machine, sometimes you can make this work like we did earlier, and it took less time. And sometimes it just doesn't work at all. So you try it again and again, and eventually it actually runs and it's faster. So this is what you can do for your clients. You can go and tell them, run my application many times in order to make it work. Clearly not the answer. So let's assume it was a smaller tree. Let's go and capture that value, because eventually we did get a performance increase, and talk a bit more about this solution. So we've done here something good, and we've done something wrong as well. So what we did that was good is we partitioned our work. We must be able to partition our work in multiple small chunks. What was bad is that the unit of partitioning was also the unit of scheduling on the operating system, a thread. And threads are expensive from a memory perspective, as clearly you saw. So that's the prime reason that you don't want to use threads in a fine-grained parallelism scenario like this. There are two other reasons. 1,023 threads, you're putting a lot of pressure on the Windows scheduler, and you're getting an unfair advantage over any other application on the system, because more of your threads are running. And it's also not the most optimum way to get the performance, even if you had the memory, because all that context switching is costing you time. So what you really want is a unit of partitioning, a lightweight unit of execution, and then maybe a user mode runtime that manages those threads for you and creates the ideal number of threads. What would be the ideal number of threads on a quad-core machine? 4. Any more and you're in context switches, right? So you want a lightweight unit of work and a user mode runtime to look at the threads. And I wouldn't be saying that's what you need if it wasn't what we have. So here I'm introducing the first new .NET 4 type, which is we call task. And if you notice here, I'm just replacing the word thread with task because the programming model is fairly similar. So I've created that. The only place it complains is down here because we have a more natural method here instead of join, which is wait. Wait for the task to complete. And now this thing builds in the same way. When I go and run this guy up, we'll see that it's going to use 100% of my CPU, but it's only created 4 threads to do that. And the time it takes beats anything else that you've seen before. Okay, so let me go back to the slides, and we'll come back to this demo, the same demo in a minute. Oh, and before I go on, can you see the elephant up there? Some people say concurrency is the elephant in the room. I say we should start addressing it from the tasks. Tasks and tasks. I thought it was funny. Okay. So I mentioned there a user mode runtime. And as soon as I said the user mode runtime that manages threads, all of you should have been thinking thread pool. And indeed, we have the CLR thread pool engine, which we had in previous versions and will continue to have in future versions. And what we have done is we have taken that engine and enhanced it. And these enhancements are only available when you go and use the task-based API. So what are the enhancements? Well, let's look at the scenario. In your program thread, you go and create a couple of tasks. And those tasks go to the global queue. At some point, in the thread pool, we have, let's say on a dual-core machine, 2 threads. They're not doing anything. They say, oh, there's work for me. They go and pick the work, and they start executing it. So far, it's all the same. Now, at some point, task 2 will maybe create other tasks. What does that mean exactly? Like in my example, whenever we did recursion and created another task, that's considered to be created in the context of an outer task, right? So at this point, task 2 creates a task, and that now goes on a local queue that we're introducing per thread. Why is that good? That's good because there's less contention when you go to a thread, to a queue that a thread effectively owns, right? So that's one performance improvement we have there. At some point, task 2 will complete. What does a thread do? Well, it wants to execute more work. It goes to its local queue. Again, no contention there. Pulls it down, and it starts executing the task. Notice that it actually pulled the last item in the queue. This is good. The last item that was created, the data it will need, is probably still hot in the cache. So this algorithm is very good for locality. So that's another very good improvement in this and the enhancements that we've added over here. At some point, the other thread completes its task. So what does it do? It goes to its local queue. Nothing there. It goes to the global queue. Nothing there either. Do we want this to be sitting idle now? No, we don't. And that's why we have work stealing. So this thread goes to the queue of the other thread and steals, stealing is a good thing in this context, steals a task and executes it. And where did it steal it from? The back of the queue. Why is that good? Well, for starters, again, less contention if one goes at the back and the other goes at the front. But also, the data for that task is probably called in the cache of that core anyway, so moving it to another thread, which is executing on another core, is not such an impact. So these are the enhancements that we have done to the CLR thread pool engine that you can only take advantage of when you use tasks. Of course, at this point, if this task created another task, it would end up on its local queue. So you may be thinking now, wow, that's a great reason to use tasks. Much better performance. And you wouldn't be wrong. But there's an even better reason. The real reason to use tasks is the rich API that they have in addition to the really good engine under the covers. So let's go and have a look at this rich API. And what I'm going to do is I'm going to give you a glimpse as to what kind of APIs we have so you can look at this further because you do have the bits on your hard drive. So it's not going to be a full tutorial. So we're back here to the example we had earlier. Well, since the cursor is there, you see here how I was waiting on the left and the right? Well, if I had many more, this would be tedious. So what you can do is you can just go here and say task dot, and we have some static methods here. And one of them is wait any, which is really cool. You can say wait for any of these tasks to complete. When it does, move on. In our scenario, the equivalent is wait all, of course. So I can go here and say wait all left, wait all right. And this is now functionally equivalent. I said that tasks are a lightweight unit of work. So if I go and create another one here, will that be worse? Let's go and see. So first I'll create this using task start new. So previously I was creating a task and then starting it, mimicking the thread creation and thread API model. Here this is mimicking the thread pool model, if you like. So I'm creating and starting in one shot. So I'll say start new, and just for difference we're going to use an anonymous method here, just so you can see that as well. And let's go and hold the reference to this guy, because I can do that, unlike with a thread pool queue user worker item, for example. And then if I wanted to wait here for this, I can do twait. We know that already. So if I run this, this is functionally equivalent to what I had earlier. Will this be slower, faster, the same? What do you think? What do you expect? And indeed, it is the same. It happened to be faster, but that is the same in the way we're measuring things over here. So that's really to hammer home the point that tasks are lightweight. You can create these things. You shouldn't think of them as threads, which are heavyweight things. Okay, what else can we do here? Well, here is a single method I'll introduce you to, which is really, really powerful. And that is continue with. So if I go here and say continue with, I can effectively go here and use another task and say that this task, whatever I've given the delegate of this thing, should execute after the previous task completes. So I could go in here and say done, for example, just for the demo purposes. We have T already. That's fine. We'll have a TT. And if I go and run this now, you should see after we wait, we'll see the elapsed, and then we're going to see done. But just so we can really make this obvious, we know this takes 4 seconds approximately. Let's make that take 2. And what do you expect to see here? If we go and run it, we're going to see first elapsed 2 seconds. Still 100% CPU usage. We see done when the CPU usage goes down. Just to demonstrate what continue with does over here. And the continue with enables you to implement the pipelining pattern, for example, and many other powerful patterns as well. And you should see that there are more configuration options. So I could say continue only when it's failed, completed only when it was successful, and so on. And I could hook up many continue withs and create a chain of events or multiple continue withs on a single task, and so on. So it's a pretty powerful method. Go and explore that in your bits. Now, when I waited over here previously, and in my first example, you saw that when we wait, all the tasks that were created as children of the original task, they had to complete as well before the method returns. So we have this concept of a parent-child relationship, which is also quite powerful, that if you create tasks within the context of another task, the outer task completes only when all its children complete. If this is something you want to get away from, we can do that as well. So there are more options when you go and create a task. You can go and pass some task creation options in and say detached, for example. So if you had a scenario where you wanted to do that, go and look at the task creation options. Many other options here, and we will be adding more. I just wanted to mention, not explain, self-replicating. It's an advanced concept, but when I show you later on things like parallel for, that's using self-replicating tasks under the covers. So that's just a heads up. Over here, I'm going to go and say respect parent cancellation. It's written creator, but it's pronounced parent cancellation, because that's what it's going to be in the final bits. So let's go and take this thing here. Let's use the same thing over there. And I want to show you now cancelling. Since I'm saying respect parent cancellation, you should know that we've integrated cancellation deep into this API, because we know how hard it is to implement that usually when you use multi-threading. So if I go here, you'll see we have a cancel and wait. You'll see we have a couple of Boolean cancel properties. One to say if it's actually canceled. One so you can see if cancellation was requested. So the cancellation is deeply built into the API. And just to demonstrate what I'm sure is the way you expect it to work, if I go and say cancel there, what's going to happen now? As soon as we hit that line, immediately we're going to see done and the CPU usage going down. So let's see if that's the way it works. 100% CPU usage, and then after 2 seconds, no more work to done, and we see both of those at the same time. So cancellation works the way you would expect it. Of course, cancellation is not using thread abort or anything evil like that. cancellation here is cooperative. So if a task hasn't run yet and you call cancel it, it won't be scheduled, it won't be run in the end. And if a task is running and you call cancel, then it has to check the Boolean property and say, okay, I'm going to stop my work then. So it's a cooperative cancellation model that we have built in here. So that's some of the APIs that we're introducing. What do you think? Do you like this stuff? Is it good? Well, if you like that, you're going to love this next one. So let's go here and make a couple of changes. So what I'm going to do is take the walk tree, and I'm going to go and comment this out. And then now I don't have a walk tree method, and I need one for this to compile. So let me go and find one that I've got down here commented out. Wouldn't it be great if whenever you want to write code, it's just waiting for you there? Control X. Let's bring this guy in. So what have I changed? Now walk tree returns an integer, which means here we must return 0, which means down here I'm returning the process item that I get from tree data. So now this is being used. And I'm also returning the results from left and right when I go and iterate through it. So what are we all thinking now? How is he going to parallelize that? Well, let's go and see what changes we need to make. And let me run it so you can see it actually running in action. So we'll go here and say int tot is equal to walk tree, passing in the tree. And let's put the result out so we can see what that does as well. So is this going to take longer, the same, less? What do you think? Let's spin it up. Of course, we're back to a linear scenario, so that's 25%. The time it's going to take will be the same. We haven't added much overhead in there. But we're also going to see an additional integer, which is the result, the total of the processing all those nodes. And let's go and capture that result. So it took 15,031, approximately the same. And the result is 9217. Let's capture that as well. OK, how do we go and parallelize that? Well, let's look at the problem by revisiting the solution we had earlier, because it's not that much different in code. So let's comment this guy out now and go and uncomment the previous version we had down here. So select all of that. Control KU. So we need to return an integer. That's fine. That's easy. That means returning 0 here. That's easy as well. Return here. That is fine too. But I also need the left and right-hand side, the results from that. So I need something here. And I need something here. And don't get alarmed. This isn't some new C# syntax. I just don't know what goes there. That's what I'm saying. So what is it we must solve? Where is the problem? The problem is that walk tree over here now returns something. So where is the natural place for that to be stored? In the task itself, right? But we need to always be able to tell the type. And in this case, the type is an integer. So it'd be nice if we had a generic task. And that is what we have. So if I go here and say future event, again, this is spelled future, but it's pronounced task of event. And I go and put that in here. Now what we've got is the results of that will be stored in this generic task, which is in the same class inheritance hierarchy as the task. So everything you can do with a task I've shown you up to now, you can also do with this guy over here. Additionally, what I can do is I can go up to this and say, well, give me the value. And I can do, of course, the same for the other guy. Of course, what's going to happen here? Well, the value was stored, so I get it back, and life is good. If it wasn't, if it hadn't executed, because these things are queued, if it hadn't executed, at this point, it would actually wait for it. So you'd be blocking on here. What does this mean? We don't even need this line anymore. And deleting code is always a nice thing. So that goes away. And if we go and run this guy now, just so we can see it in action, we'll see that we have 100% CPU usage. The sum will be, of course, the same. And, of course, again, it takes the time that it took earlier. And with that, let's go back to the slides. So we saw there the rich API of tasks, and earlier we explained the engine under the covers. As a summary, like you used thread pool queue user work item today, a fire and forget mechanism, no handle to get back, none of the rich API things you can do with tasks. You can use tasks in that manner, but you can also use them in all the other ways that I showed you. And the parent-child relationships, continuation, waiting, cancellation, task with results, these are not the entire API. We have more in there. Play with the bits and you'll find them. And we're also going to be adding more later as well. So to conclude this section, which I called fine-grained parallelism, just so we can make sure that the big message is there. What we need to do is we need to partition our work into multiple chunks, like 1023 I was using here. Why? You may be thinking, why, on a quad-core, you just don't partition your work in 4 chunks? Well, if I did that, it would be bad for 2 reasons. One, when we then move our code to an 8-core machine, we're not using the other 4 cores, or a 1000-core machine, all those other cores are sitting idle. So we need to write our code once and have it scale as the hardware gets better under the covers. That's why we need to partition into multiple small chunks. The other reason we want to partition into multiple small chunks, if we partition it into 4 chunks only, and one of the cores finishes its work, it now can't steal any work from the other ones, so you're wasting it. It's just sitting there. So for these 2 reasons, we need to be able to partition our work into multiple chunks. And we need that to be in lightweight chunks, while we still have only a number of threads equal to the number of cores. And it is for that reason we need fine-grained parallelism. For that reason, we need tasks. So that concludes this first, and for me, the most important section of what we're going to see in this session. Are you all still with me on this? Yeah? That's good. That's good. So when we go and look at structured parallelism and declarative data parallelism, things get much, much simpler immediately. And you're going to really like that stuff. But before we go and see more code in those sections, I thought I would share with you the really cool new enhancements we're adding to the debugger. So we have 2 new debugger tool windows, and I want to show you those now. The goal of the debugging support is not to kill bugs. No bugs were harmed in the making of this presentation. The goal we have is to make task-based programming, so tasks, a first-class citizen in the debugging experience. So what I have here is another console application, single file in here. And in this time, the code is not important. I can show you the entry point. I go in here and create 4 tasks, and they all start live in the M method. And I'm passing in, because you can pass in values as well, I'm passing in the state, which is 6, 7, 8, and 9. So here's my obfuscated code. That's the way I write code usually. So it's all single letters. And it's not important what's in them. What we're going to try and do is follow the code path that those 4 tasks take without looking at the code. So the first pass, we're going to hit 4 breakpoints, each time trying to figure out what has happened using the existing debugger tool windows. So let's go and do that. So I'm hitting F5 here, and we've hit our first breakpoint. So now I have to see how many tasks have I got, where are they? We know tasks get executed by threads. We also know this is a quad-core machine, and I queued 4 tasks. So I could go in the threads window and find it. So this is extra knowledge you have to have, but you know, like I said, I'm a trained professional. So we get in here, and again, because I'm a trained professional, I can see that these 4 here probably correspond to my tasks. I had to make that jump. And I can see from the call stack, this particular one started life in the M method, and then went to O. Okay. If I go here and double-click, the whole context changes. I can see this one also started life in M, and then went to O. Let's go to the third task. Oh, same story. And you can see my locals window updates when I switch, obviously. And here, the other one as well. So all 4 from M went to O. Why did I have to double-click all over the place to see that? Why couldn't I see that in just one view? Let's store that thought. Let's go and hit the second breakpoint. Here I can see that now one of the tasks from MO went to IC. Okay, IC. Let's go and look at the other one. This one has gone from MO to TH. Let's go and look at the other one. That one also from MO to TH. Oh, and that one also from MO to 2H. So 3 of them went one way, and the other went the other. Again, all this double-clicking. It's not efficient. Let's go and hit the third breakpoint, which is a bit of a mystery, so you'll need your thinking caps on this one. So now let's go and look at the tasks. One of them, MOIC. That's where it was before. Fine. We had the other 3 in the same place. MOTH, that's the same. MOTH, that's the same as well. Oh, what happened here? One of them that was in MOTH suddenly now seems to have been reborn and appearing in D. What has happened here? You cannot really have a definitive answer to this without looking at the code. Right? So the windows are not helping you. Store that thought, and let's hit the 4th and final breakpoint. So now I'm going to the final breakpoint. I double-click where I did earlier. Oops, that's not the task. Oh, that's not either. So now I'm playing the game Hunt the Task in the Threads window. Not a great game to be playing. And if I go here, MOTHFG, fine. Let's look at the other one. MOTHEKG. So maybe I have to do a couple of double takes to see where they diverge and where they converge. Not ideal. Let's stop this and go and look at the new stuff that helps us with all the questions I've been raising. So we'll start it again, same application. For starters, Why go to the threads window to find tasks? Why not look at the parallel tasks window? There we are. Here I can see IDs for each task. These are IDs of a task. And if I want to see what thread they were on, I also have the thread IDs they were on over here. I can see that all 4 of them are running, so I can see the status of them. I can see where they are right now, so I can see information on the location. And if this isn't just a picture, I can go and actually interact. So if I double-click, you'll see the rest of the ID updates. And the threads window has also synchronized to where I am as well. So it's fully integrated into the IDE. And as I double-click, I can go and look at the call stack window and find where they went. But why do that? Why not go to the debug windows? And you see here parallel task. That's how I brought up that window. But there's also another entry here, parallel stacks. Well, have a look at this guy. So this tells me you have 4 tasks. There are the IDs for those 4 tasks. And they're all sharing the same method context. All of them went from M to O. And when I hover over, you can see in the rich tooltip the actual stack frames for those 4 tasks. One picture, a lot of information. Let's go and hit the second breakpoint. What happened at the second breakpoint? Do you remember? 3 of them went one way, 1 stayed the other. It's very clear now exactly what has happened, and I can see where they actually went their own ways. So maybe this is exactly what I was expecting, in which case, fine, it has been confirmed. Or maybe that's not what I was expecting. So where do I want to go? I want to go in here. This isn't just a pretty picture, it's interactive. So I can go and switch to this, to either on the current thread or maybe some other one, and the whole IDE updates. It's integrated into the IDE. And now I can see O method here in my code editor, and I can see what has exactly happened, how they actually went their own ways. And notice that when I go here and actually switch to a frame, the rest of the IDE, the task window, the locals window, the coder, everything updates at the same time. So let's go and find the third breakpoint, the mystery one. Keep an eye on the task window. It's not a mystery anymore. I actually have 5 tasks, not 4. Another task was created. And where was it created? Well, it's a child of task ID 1. It's very obvious we have here the parent-child relationship, which I can collapse if I don't want to look at. So that's why we're seeing one of the threads be somewhere else. This is on the same thread. The thread was executing a task. The task went in waiting. We're reusing the thread. We pulled the other task down, and now executing that at this moment in time. So no mystery now there anymore, immediately obvious without any more clicks. And let me go and hit the fourth and final breakpoint. That's when we were playing hunt the task in the threads window. No more hunting. It's immediately obvious. 2 tasks. Obviously, all the rest have completed. They're no longer active. And I want you to notice on this side that when we go and select a method here, switch to it, it becomes bold. And if what you make is a method bold that also appears somewhere else, we make it bold everywhere. So if you're trying to see where a method context is being executed by multiple tasks or threads, then that is immediately obvious. And if you do want to switch on a method view, that's what your focus is, that's what your pivot is, then you can go and do that. And now I've brought all the methods together. And you can see the callers and the callees in one picture. And you can go and switch here and continue doing that. You can, of course, go back to stack view. And notice here we have a threads tab. If actually you're focusing on threads, you haven't adopted the new APIs, you're using just traditional multi-threading, you can still use the parallel stacks window. And now you can see the main thread in here, for example, as well. Right? Finally, if we look here, it's okay. And before I go back to the slides, you see we have here flagging. So I could go here and select flagged only, so I can filter down if I have multiple threads, multiple tasks, the view that I have. I'm really excited about these windows. If you have any feedback on anything on this session and on these windows as well, then by all means, do email me at daniel.moth@microsoft.com. So what did we see there? We saw the parallel tasks and the parallel stacks window. These are available both in managed and in native. So we don't discriminate. We support both schools of thought. You saw the parallel task window had the waiting and running status. Also, what you didn't see there, because I only had 4 tasks, if you create more than that and they're in a queue, we'll show those as scheduled in red, like the screenshot shows. So you'll be able to see what load you're putting on your engine effectively. And like I said, the parallel stacks window also usable in just straight threading scenarios, not necessarily with parallelism. So what do you think of that? Was that cool? We like that? Great. Fantastic. So that concludes showing you the debugger support, and we're going to now go and look at structured parallelism. So now things get really, really easy. I mean, they're so easy, you'll see. So what do we mean by structured parallelism? In a very simple way of thinking about this, you can think of this as blocks. You have a block of code that you need to parallelize. So what happens in this block is one thread goes in, multiple threads, multiple tasks execute your code to achieve parallelism, and then one thread goes out again. That's basically what we mean by structured parallelism. You have already seen how you can achieve structured parallelism. If you create a task with a delegate and you have the body, any task you create in there, you have structured parallelism. So you could do that already. What I'm going to show you now is that we have taken and implemented some higher level algorithms which provide solutions to common problems that you have when you try and parallelize certain pieces of code. So let's go and have a look at the demo. So I'm going to bring up here another Visual Studio 2010 solution. Again, it's a console application, single file. And what do I have in here? If we go and look at the entry point, it just calls do it. And we have a stopwatch, again, measuring how long that takes, and then we wait. So what do we do in do it? Well, in do it, I'm using this array of strings. And what I'm going to do is go zip through this array, and then go and put on the console what item I have found, the string. And also I'm going to call TID, which is the thread ID. So I'm getting the current thread ID there and sticking it out on the console just for information. But also what I'm going to do here is some business logic, and I'm simulating some processing. How am I doing that? I'm spinning pointlessly, right? This is where you would have your real code. So let's go and see how well this performs. How long does it take? So we run this guy up. We can see the strings that printed out. Obviously, everything is on thread ID 1. It's single-threaded. And we can see it takes quite a bit of time. In particular, it takes that long, 8822. Let's go and capture this. So I've set my performance goals beforehand. I look at the results. I'm not happy. I need to optimize this in order to ship it. So I go in here and try and optimize this, and you know the deal by now here. We can't optimize this. So I have to go and find another way. So it's back to the drawing board. I have a single chunk of code that I need to partition. It's a natural partitioning thing here. I've got iterations. And since each iteration is independent of any other, and it doesn't depend on any shared state, that means I can go and easily use tasks and parallelize this. However, this is such a common problem that we are offering you a much easier solution than having to think in tasks. So what is that solution? Well, what we can do is go and say parallel dot for each. And then in here, it says, what is the source? Well, the source is R. And then it says, give me a delegate. Well, the delegate is going to have some arguments. That delegate is going to be string IP. And then I'm going to go here and say this. And then I need a body. It's a good thing I have a body up here. So I'm just going to Control-C that and Control-V it over here. And then this is a method call, so I have to close the method call, and I'm done. Now, let's comment this out, because I know what you're all saying. Prove it. So let's run this guy up, and there's the proof. Two, 2, 4, 5. Wow. Linear speed up over here. And if you look at the thread IDs, like I was saying earlier, just 4 threads executing this piece of work over here. Now, if you have something more complex, how would you address that? What do I mean by more complex? Well, let's go and do this. What if here I was doing some kind of searching? And what I wanted to say was, you know what? If the string that you have contains 3, and you still need to close strings. We haven't changed that aspect. Then here I want to go and store that in a result, which I'm going to have to declare in a minute. And then break, because that's what we do in loops. So let's go and make this compile. And run it up, just so you can make sure you know what's going on here. So we're processing everything again in the same way. How long it takes doesn't really matter here. But as soon as we find the string that contains 3, we break out. So how can I go and make this work? Well, let's go and have a look. I have this construct over here. And what I really want to do is take this. So let me Control-C that and stick it over here. And let's go and comment that out. Will that work? Will that compile? No. But thanks for playing. So you win a book. Come later. Whoever said yes. I've got books here from Joe Duffy. You have a book. But that doesn't mean everyone else will start answering wrong. So we have here, break will not compile, because break is only applicable in the context of a loop. And even if we did some magic and made it do that, what would it break? We have multiple threads in here now. Which one would break? So that doesn't work. What I need is something else. And that's why we have different overloads here. I can go here and say, put inside the parallel loop state. And then in here, I can go and say ps.stop. And you saw there were more options there. And what I can do here, just to be even more efficient, is say, if not, ps is stopped. Only then go and do that. And now if I go and run this guy up, you'll see that it just completes immediately, right? And we made it work. What's my point here? So the point here is not just to show you the break, but go and explore the parallel for each. It has 6 overloads, and we're doing more work there. You can configure this much deeper. Just because we have an easy entry point doesn't mean we take away any of the flexibility. It returns parallel loop result. Just go and explore that in your own time. Before I go back to the slides, you should go and look also on the parallel, the invoke method, which takes an array of actions. So you can go and pass in an array of statements. So this is typical fork join parallelism here. You have multiple statements. They're now going serially. You want to make them execute in parallel. You can just pass them all in to parallel invoke, and it will do that for you. So that's the advantage there. Remember earlier I showed you the ray tracer example, and we had the checkbox. I have this on this machine as well. And when we check that checkbox, what we do is actually very simple. We have render sequential and render parallel. Look at the body here. These lines of code I've highlighted in the render sequential are identical to what I have in the render parallel. The only thing that changes is the top thing, parallel 4. Start at 0, go to screen height using Y. Start at 0, go to screen height using Y. It's almost automatic translation. So very powerful for structured parallelism. The parallel helper methods, check them out. Let's go back to the slides. I told you things would get much easier, didn't they? Yeah. Cool. So, one item left to go. I call this section structured parallelism, but you should not be thinking about these different sections as separate entities, right? So, structured parallelism, but actually we could have done that with tasks. And in structured parallelism, we can use fine-grained parallelism under the covers. So these are concepts you can mix together. Specifically, when I showed you the parallel for each, we also call that imperative data parallelism. And that links to the next section, which we call declarative data parallelism. How can we do declarative stuff in the managed world? Someone said it? Link. How many people here are familiar with link? I have to check that. Okay, most of you. And those of you that aren't, don't worry. So here is a link query up there. This is how we do declarative parallelism, by taking link queries like that and making them go faster, making them take advantage of parallelism under the covers. Those of you that know about link will know there are 2 flavors of link, really. There is the link to iQueryable sources, which use expression trees under the covers. Examples of that are link to SQL, link to entities. That is not what we're talking about here. The other flavor is link to IEnumerables, such as link to XML, link to datasets. Anything linked to any in-memory object collection. That's the link we're talking about here. So if I have this query, how can I go and make this go faster? Right? Minimal impact to existing link model, it says. Keep an eye on that code on the screens, because if you blink it, you'll miss it. That's all you have to do. And you're probably thinking, prove it. So let's go and do that. So I'm going to go and reuse the existing solution here, but actually switch out this file for another one. So for all intents and purposes, it's a different project. And you'll notice here that I'm referencing system core, which is where link lives. And if we bring this guy up, what are we doing in here? Well, I have a main. It calls do it. We have a stopwatch, and then we see how long that took. So my imagination is not that rich. I keep reusing the stuff. So what do we do in do it? Well, in do it, we're going to use is prime. So I have here a naive implementation of is prime, but it doesn't matter. The point is that I'm not spinning for a change. I actually have something. And this is going to do something which is computationally intensive. And depending on the integer you pass in, it could vary. So the workload would vary here as well. So how am I using is prime in the do it that I'm calling from main? What I do is I go and create this small array of 4 million items. So it has 4 million integers. And I go in here and just say from everyone in there, check if it's a prime. And if it is, I want to add it to my collection, but as a string. So I go and call to string on that, which means here I have an IEnumerable of strings. Of course, there's deferred execution here, and this is still true. So when I call toList, that's when we get the actual list of strings here. And what I'm going to put out on the console is the count, how long that took. So let's go and run this guy up. If I showed you Task Manager, you would see 25% only, because this is sequential. And then we're going to see that it actually takes 4352. Let's go and capture that. 4352. And you can see the result, 283146. I'm sure you'll remember that. So how do we parallelize that? Well, you've seen the answer on the slide as parallel. Control F5. Now I'm using 100% of my CPU over here, and you can see it takes 1186. So before I go back to the slides, if you're a bit like me, you're probably thinking, wow, magic. How does that magic work? So let's have a quick look at how this magic works. So if we take this query over here, and I'm just going to Control-C, Control-V it, and do that over here. Name this Q2. That query up here is the equivalent of doing this. And as I say, I hope you know this. I can go and say r.where, so I'm bringing the extension method. Then I use a lambda and say is prime of n. And then I go here and say select, and in there give another lambda where I'm saying give me n to string. And if I go and place here carriage returns in places where carriage returns are not supposed to be placed, you'll see that actually it does look very similar to what I had up there. These two are equivalent. This is not new. This is how LINQ works. So exactly what happens here? Well, I have my source. IEnumerables don't have a where method. This is an extension method. And if I go to definition on this guy, you'll actually see that what we have is the enumerable class, which we introduced in .NET Framework 3.5, which has a whole bunch of extension methods, there's the this, on IEnumerable. So what happens when we go here and say as parallel? Well, when I say as parallel, and I put a dot, the whole thing still compiles. So what has happened? As parallel, all it does really is a smart cast. It takes your IEnumerable and casts it to an iParallel enumerable interface that we're introducing, which inherits from IEnumerable. So that's why the whole thing still works. So why are we doing a cast? Where's the value? By doing a cast, these extension methods are now our own new extension methods that live in a separate class we're introducing, the parallel enumerable, which has extension methods to iParallel enumerable. So by bringing in our own extension methods, we now have our own implementation running on your queries. And guess what we're doing in our own implementation? What are we using? Tasks, right? So that's how this works. I just thought I'd give you a glimpse into that. Now, like I showed you with Parallel 4, I don't have the time to show you everything over here. However, you should know that we have more tweaks and knobs. So you can go and say as ordered, because when you say as parallel, the results and the processing won't happen in the same order. So if order was important to you, then you need to put as ordered in order to configure that. So that's like a little knob that you have over there. And you can see there are other methods in here as well, like as merged. And again, just go and look at these in your own time. You have the bits on your hard drives. So with that, we're going to go back to the slides. So that was P-Link. And that concludes the stuff I had on the agenda to show you, but I have a bonus item. Coordination data structures. When we built these libraries, we actually needed some new synchronization primitive stuff that exists in the literature but didn't exist in the .NET framework. So we introduced all these types you see in white, and we are using them, and we thought, let's make them public in .NET 4 so you can use them as well in your parallel and multi-threaded applications. I don't have time to go on a demo and show you this stuff, but I thought I'd point them out to you. Go in MS-Corlib and System, and you'll find them there, such as safe concurrent collections. Have a look at those and play with them. So in summary, I'm just going to take 2 minutes to summarize, and then I'll open it up. This is the list of things that we have in Visual Studio 2010 and .NET Framework 4 for managed developers trying to take advantage of parallelism. You've seen most of those in this session here. But that's not the takeaway that you should be taking back to your colleagues and your managers. The real takeaway here is embrace parallel programming, because in the future it will be essential, and right now it's very important. And our end goal here is to create brand new user experiences. Everything I showed you was about making compute-bound operations go faster. And that's the first baby step on your existing code bases. The real goal here is to actually create new applications that we can't even imagine today. And when I put this presentation together, I had some examples of the things you can build. But then I thought, no. When we moved from DOS programming to GUI programming, could anyone imagine what we could do? When we move from classic GUI applications on a desktop machine to applications that have internet connectivity, so the software plus services world, could we imagine back then, before the internet, what those applications would look like? This is another such shift in the computing industry. You're going to have unprecedented compute power on the machines. If you use parallel programming, you can take advantage of all those cores and do things you can't imagine doing today. And that's the end goal. How do you get there? Well, you start playing with the bits we're giving you now and the bits we'll be giving you in the future. The first step was coming to the session, so I thank you for that. We have other sessions throughout the week. Some have taken place, some will take place. Go to those as well. And if you've had enough of sessions and you just want to get the bits and play with them and maybe see some articles and stuff in your own time, visit msdn.com/concurrency. A lot of material up there for you to go and look at. And like I said, everything is on your hard drive, the Visual Studio 2010 CDP, which is what I've been using over here. So with that, I'd like to thank you very much for investing your time to come here. I hope it was a useful use of your time. Thanks. Fill in your evaluation forms. Thank you. For those of you leaving, if you have any questions, you can email me, daniel.moth@microsoft.com. And for those of you staying, I can take a couple of questions now if you want. Yes? The question was, I don't think the mics are turned on, the question was about handling marshalling to the UI. You have to do that yourself, but we will offer you something that's going to make it a bit easier to do that as well. So we will help you there.
Okay. Last two questions. Is the pool per process or per app domain?
I didn't get that.
Is the thread pool you're drawing from per process or per app domain?
It's the classic thread pool that you have already. We haven't changed the aspect of it.
Okay. And is this going to be available in the .NET Compact framework as well?
It is not available in the .NET Compact framework that gets released with Visual Studio 2010, but we are talking to those guys for the future. And for asking that Compact framework question, you've won a book, so you can come and collect that. Yes?
Are you going to be providing any native support for bindable data structures so that the application doesn't have to do all the marshalling under the covers?
So I think the native guys are looking at that. I don't know if it's in there already. But so that's a question for the native.
No, I'm sorry. I mean, like.
I didn't hear that. Oh, WPF, you said?
Yeah, it's like for WPF, if you're going to data bind to one of these, to a collection which is being manipulated in parallel tasks, for instance.
We're not going to offer that out of the box, but you'll be able to build it
So
yourself.
the application will have to do it.
Right.
Okay.
I saw in your demo that if a task calls another task and has to wait on it, another task can fill in its slot in that thread. Does it do the same for like IO bound blocking stuff, or do you have to provide stuff from the user side?
IO bound stuff would be the same as what you have in the thread pool today. So we're not doing anything specific for that.
Okay, does it put another thread out there so the core is not sitting idle, or?
Yeah, so the cores will never sit idle with the model.
Okay, so it'll spin up more threads if it needs to. Okay.
How do multiple applications running with this technology will compete for the resources?
The Windows scheduler will arbitrate that. So if you have, let's say, two applications using our library and a quad-core machine, one has 4, the other has 4 threads, Windows will do the third thing over there. It's much better than obviously rolling your own in each application, and then it's uneven on the operating system.
I think there's going to be some language enhancements for C#. I heard something called C Omega. And the question is, when is it going to be available? Is there a schedule for that?
I didn't get that. I think this microphone is not on very well. Can we turn it up? I think you asked something about language enhancements.
Yeah, I was asking, there's going to be some language enhancements for C# specifically.
Right.
I heard something called C Omega.
That was a research language from the past. So in this release, we're not integrating with a language, but this is definitely something we're looking at in the future. I mean, you could imagine having a P4 structure, for example, that does kind of the same thing. You can imagine that. That's not what I've seen anywhere working, but it's something we're thinking about, integrating closer into the language. Not in this release, and the benefit is because we're a library, any managed language can use this stuff.
Okay, thank you.
Okay.
Is there any multiple classes of tasks that
Where
we
are
can...
you?
Here.
Yes.
Is there any multiple classes of tasks that we can classify, like thread, if I can create multiple thread pools, that sort of thing right now?
No, so right now the thread pool like it was before, it's only one. You can't create your own. But if you're talking about task types, the task is not sealed, so you could go and create your own tasks there.
Right, but what I have to do is I have to create my own thread pool right now to prevent thread locking, because I have some. You can't do that right now, right? Not for the task.
I don't know why you need to create your own thread pool to prevent.
Right now I have some deadlock issues that I have to put them into two separate thread pools.
Right, so the deadlock issues you have are like orthogonal to having multiple thread pools. We're not doing anything here for deadlocking. That's still your responsibility.
Okay.
With tasks, if you could end up in a deadlock scenario. Threads are not something you use explicitly. The engine does that for you. So you program in tasks.
Okay.
Right?
Thank you.
Hello. What is the relationship of this work and the work in CCR?
So the CCR is something that the robotics team have shipped. It
Yes.
also addresses some of the same problems. It's a different programming model, and right now it is separate. Our long-term goal in future versions, not in this release, in future versions, is to bring that programming model into the .NET framework, and then it would be using the same engine that I showed you here today. But right now, they're separate.
Thank you.
Okay.
What
Yeah.
are the basic differences between a thread and a task? And why did you choose not to make threads parallel, but have a new concept called tasks?
I really cannot hear this microphone. Is it possible to turn up the middle one? Or maybe I just can't hear in this direction. I don't know. It was something about thread versus task.
Yeah. What is the basic difference between a thread and a task, and why did you choose to have a new concept called a task and not make threads parallel?
Actually, I heard that better, so I'll repeat the question. So the question was, why do we introduce a new concept called task and we didn't use a thread? And it's what I said earlier on. Maybe I said it too quick. So what's with the thread is at the OS level, it's both the unit of scheduling and also the unit of partitioning. That is bad because you want to be able to partition a lot, but you only want few threads. So that's why we need a higher level, a lighter abstraction, a lighter unit of work. And that's why we're introducing task. Does that make sense now? Sure. Cool.
So, sorry. Over here.
Yes.
What about thread priority?
So thread
task priority, sorry.
Yeah, we don't have task priority right now built into the system. There will be, what I didn't show you in here was that you can write your own scheduler abstraction, like a task manager, task scheduler type. And if you wrote your own, you could do something in there to work around that. But the short answer is we don't offer that out of the box. The long answer is, I'm not going to give you the long answer. The nutshell of the long answer is you'll be able to do something on your own if you want to invest in writing that code. Okay?
Are you planning to support parallel link with link to SQL?
So if you think about what happens with link to SQL, it's really just constructing the query, and then all the work is offloaded to the SQL server, which is already doing stuff in parallel. So there isn't really that much to do there. However, if you were going to hit multiple databases, get back all the objects, and then do some link to objects manipulation on the results, that's where you could use p-link. Okay?
Thank you.
Do you think we'll see this in Silverlight?
We are talking to the Silverlight team.
Okay.
So to echo the other guy's thing about multiple thread pools, I can give you a scenario where I would need another thread pool, and the example is ASP.NET and starving the ASP.NET thread pool, which is using the main.NET thread pool. And I've had applications where a simple logging app thread, starves that thread pool, and we really want it to be low priority, off to the side type of thing. So can you address that scenario?
Sure. So I'll give you 3 very short answers to that. The first short answer is ASP.NET is on the server. On the server, typically, what you care about is throughput. So even though you can use our stuff, actually there you're already taking advantage of your cores as long as you have more client requests than cores. So that's the first short answer. The second answer is that what I said earlier, if you write your own task scheduler, it's harder, but you may approximate what you want to do for many scenarios. And the third answer is if you have a very specific scenario you'd like to discuss, please come later. The team is here, and we can discuss your request and see how we can incorporate it. Okay?
Are fibers anywhere in this picture?
No, fibers are not in this picture. Fibers eventually run on threads, so threads is what we're using. We're not using fibers over here. So, okay. No, they're not.
I was wondering, what is the smallest amount of work you want to parallelize? It takes some time to start up the scheduler, I'd imagine. So what is the smallest amount of work you want to parallelize?
That's a good opportunity for me to say measure. You got to measure it yourself. So you have a piece of work, to partition it as much as you can, and then measure. Are you getting the performance benefits? At some point, obviously there's overhead in using this stuff. There's some overhead to get the whole thing started. So you got to see where is the break even. Either you need a lot of data, or you need more chunkier pieces of work.
So you might want to introduce logic or business logic that determines when to offload to parallelizable or not.
I think you will probably know from the get-go when you design your solution what's the smallest unit of work in your application that will work. I don't have here guidance as to how many cycles it is worth going parallel because we haven't shipped yet. Once we ship, we may be able to make comments on that front. It's so many cycles, it's worth using a task. Less, you might as well stay sequential. Okay.
So the documentation says that there isn't a one-to-one relationship between CLR threads and OS threads. Has that changed with 4.0, or has that never been true? Or
the documentation has not changed.
So there still is not a one-to-one relationship between threads and the CLR?
The reality is that we can change that at any moment that we like, but right now it hasn't. As far as I know, we're not changing it.
Okay, thanks.
Have you thought anything about affinity of tasks, like if you have cores that are good at different things and so on?
The idea is that you really don't worry about that because we're doing it. So we're thinking about affinity in general, but we go towards the end of, you don't have to worry about that. You shouldn't have to worry about that.
Okay.
Do you see any opportunity for parallelism in things like XML serialization, parsing?
Yeah, anything that is compute bound, there is opportunities for
So is there going to be a library for that?
So we are offering the library so you can use it, and also other internal teams at Microsoft can use it, and indeed there are many teams that are interested. I don't think they'll be able to use this in .NET 4, not all of them anyway, but in the future you should expect to see that. Okay, well, thanks again. You can always catch us here and also catch us at the stand. Thanks.